All right, guys. Two more things to talk about, really. Points of inflection, the second derivative test. And a point of inflection is where the thing changes from concave up to concave down. If you remember this picture we saw up here where I was like, where does it change? You can't really tell. Well, the places where it changes are called the points of inflection. If this graph was the way I said it was, and it changed at x4 and x6, then the points of inflection would be x4 and x6. That's where the graph goes from concave up to concave down, or from concave down to concave up. More mathematical definition is that, I mean, that's exactly what I said. The concavity changes from down to up. So this is kind of like a way to think about it, down and up. And if I put them together, the place where they meet is called the point of inflection. So this is just the way that this is just another definition of concavity. I'm honestly not sure why this slide is in here. The second derivative is positive for AB, then we say f is concave up. That's just what it means to be concave up. And if f double prime is negative, then we say that f is concave down. And the way we test for inflection points is pretty much we look at where the second derivative is equal to 0, and then we see if the second derivative changes signs there or not. And we'll see how to do that in a minute. But like it's important. Like you do this, and then we got to check and see if this is true or not. This is like step 1 and step 2. The other part of step 1 is step 1a. We also got to see, is there any place where the second derivative is undefined? It's kind of like finding a critical point. You check and see where the second derivative is 0, and you see if it's undefined, then you check and see if the second derivative changes signs in those places. This is like kind of like a summary table of sorts, just so you know what the pieces look like. If the function, this is like if the function is for f, for some function f. If it's increasing in concave up, then it looks like this. If it's increasing in concave down, then it looks like this. And if it's decreasing in concave up, it looks like that. And if it's decreasing in concave down, it looks like this. And then I think the point of this guy is to like put these little pieces in here and tell you, like, let's think about what that means for these other functions. So I got this one, this one, this one, and that one. And this one is increasing, so the first derivative is positive. That's concave up, so the second derivative is also positive. So I want you guys to like fill in this table with all the rest of the pluses and minuses. I'm actually going to leave that as an exercise for you guys to do, and we can talk about it in class. Second derivative test is like the last concept in here, which is like once you've found all the critical numbers of f, we've done the first derivative test, which is where you do the first derivative test is like you do the sign chart with all the different values, all the different critical points you found, and we put in a bunch of minuses and a bunch of pluses, and that tells us if they're maxes or mins. This is the first derivative test. Second derivative test, you just plug the critical points into the second derivative, and that tells you something. And it works because if I have this point, this critical point here, and like this is clearly going to be a max, but this is concave down. Anytime a critical point happens on an interval where the function's concave down, you're going to get a maximum. Right? The concave down is the key here. Concave down functions look like this. Like there's no minimums happening on this interval, it's all maximums. And the same thing here, but opposite. It's ever concave up, well, if there's a point C where the derivative is 0 in here, it's got to be right there at the bottom. All right, this is where the C's happen. And so like if it's concave up, concave down, this means f double prime is less than 0. This means f double prime is greater than 0. So basically, you plug the C that you get into the second derivative, and that tells you it's a max or a min. And if you plug it in and you get a positive number, that means the function looks like this. Nope, that's upside down. That means the function looks like this, concave up. So that means that C is a max of f. And if the second derivative is negative, that means it looks like this, which is a maximum value. So that means Usually, C is a minimum of F. Looks like this, you get a max, that means C is a max of F. And it's possible that it can be equal to 0, and if that happens, then the test is indeterminate. The test doesn't tell you what you want it to. And if that does happen, then you should just use the first derivative test, which will tell you for sure one way or the other. I mean, it could be neither, which is often what happens when it's 0, but you got to use the first derivative test to check if that's the case. So here's an example of how to use, we're going to do these two examples, then we're going to be done. Here's an example of how to use the second derivative test. So first you find critical points. So we do f prime of x is 5x to the 4th minus 20x cubed. This thing is defined everywhere because it's a polynomial, but it's probably equal to 0 somewhere. So let's maybe factor a 5x cubed out and set the rest equal to 0. This gives me x equals 0 or 4. So now we can do the sign chart and put 0 and 4 and test 3 points. But because this asked about the second derivative, it said use the second derivative test, we're going to do that. So the second step of the second derivative test would be to find the second derivative, which is 20x cubed minus 60 x squared. I'll factor this just to make my life a little easier. 20x squared times x minus 3. So now you basically, you plug in 0 and you plug in 4. And depending on whether the integers are positive or negative, that tells you something that you need to know about whether it's a max or a min. So if I plug in 4, for example, I get 4 minus 3, which is positive 1. And then 20 times 4 squared. Whatever that is, it's positive. And that's all I really care about. Like, I don't actually care what the number is, I just care that it's positive. Because the second derivative test says if it's positive, that implies that x equals 4, that point I just tested, is a minimum value for f. I drew the picture here so you guys would see what the function looks like, and you can see that it is a minimum, right? And it's a minimum because the function's concave up there, and that's what this second derivative greater than 0 just told me, concave up. 0 is a little more annoying. If f double prime is 0, you get 20 times 0 squared, and I don't care what this is because the whole thing is just 0. Which means the second derivative test fails. So I do have to draw the number line anyways. My first derivative test number line. I'm going to test the point 0. Remember, this is an f prime graph. So maybe put in -1 and then put in 1 and just see what happens. So if x is -1, I get 5 times -1, that's -5, times another negative number is going to be positive. I put in a +1, I get 5 times 1, that's +5, times negative number is negative. This tells me that 0, sorry. So x equals 0 is a max. Remember, this is like positive slope, 0 slope, negative slope. That makes it a maximum of f by the first derivative test. This f dt and s dt is not, that's not lingo anybody uses except me, so I wouldn't expect anyone else to know what that means. All right, and now this is just so you guys know, if I say I find the points of inflection, that's where the concavity switches from positive to negative. The way that we find that is we find the second derivative, and then we check and see if there's any place that's undefined or 0, and then we plug, and then we use the number line, very much like this first derivative test. So f prime of x is going to be negative sine x, and double prime of x is going to be negative cosine x. I know that cosine is defined for all values of x, so I don't have to worry about any place where it's undefined. Between 0 and 2 pi, the cosine is 0 at pi over 2 and 3 pi over 2. So f double prime of x equals 0 means that negative cosine of x equals 0, which means that x is either pi over 2 or 3 pi over 2. These are values from the unit circle, I'm sure you remember. And so now I got to check and see if those are, you got to make sure those are really points of inflection. By like, you kind of plug in numbers on either side of them. Remember, my interval is only from 0 to 2 pi, so I don't want to go outside of those numbers. So I'll plug in maybe a number here, maybe pi over 4. Maybe I'll throw in a 3 pi over 4. Maybe I could put pi in for this one. That'd be easier probably. And then 7 pi over 4. That's bigger than 3 pi over 2, right? The cosine of pi over 4 is root 2 over 2, but it's negative cosine, so it's going to be negative root 2 over 2. That's a negative. Cosine of pi is negative 1, but negative 1 is positive 1. And the cosine of 7 pi over 4 is also root 2 over 2, and it's negative, so it's negative. So that checks out. The concavity, the second derivative changes from negative to positive here. So pi over 2 is a point of inflection. For f of x, because, and there's the reason I want to write out this justification, because f double prime goes from positive to negative at x equals pi over 2. Oop, yeah, 3 pi over 2 is a point of inflection for f of x, because f double prime goes, oh, I said this wrong. Why do I keep doing that? At pi over 2, the second derivative, this is the second derivative chart, goes from negative to positive. 3 pi over 2 is a point of inflection for f of x, because f prime double prime goes from positive to negative at x equals 3 pi over 2. The reason I wanted to write that out is because this is the kind of justification you need to provide if it said find the points of inflection, justify your answers. Like, you got to do this and check this, but this chart, while very illuminating, is not a justification. You have to be able to write a sentence like this or like this that indicates that you understand how to interpret the chart. So that's it. We'll do some more examples in class. Bye.